Just imagine the bottom of the slides. What is that for? Right, so these days we're all pretty familiar with voice recognition software. Well, voice recognition, right? Even if you hadn't had a chance to play around with one of these, I'm sure you've called Centrelink or the tax office or an insurance company and had the joy of dealing with their call routing system. And even before these kind of systems were so ubiquitous in everyday life, click. We knew about them from the movies, right? HAL 9000 is really just evil Siri. It might surprise you to learn, though, that speech recognition actually predates any of these things. The first speech recognition system was developed by a bunch of guys working at Bell Laboratories way back at the dawn of computer science in 1952. They were working on a system to automate voice dialing, because I guess not everyone had a Captain Crunch whistle. The system they built was called Audrey, for Automatic Digit Recognizer. It could recognize the digits 0 to 9, and it got 97 to 99% accuracy, which you can see clearly there. To put that in perspective, Google's voice assistant or voice recognition software hit 95% accuracy in June this year. So how did that work? How could a system that was built 60 years ago compete with the top of the line today? Well, the answer is it's a trick, pretty much. And to understand how that trick works, let's have a look at how Audrey actually worked. I couldn't find a picture of any of the scientists who actually worked on the system, so I've kind of gone with random computer scientists. This is Alan Turing. So if Alan wanted to use Audrey, first of all, we need to tune the system. You can think of tuning as being kind of analogous to the training that you might do with a more modern system, but there were no machine learning algorithms in 1952, right? When you went in to tune the system, you had to change the hardware. You had to go in and flip the relays and turn the dials and do whatever it is one does with vacuum tubes. But we can get a basic idea of how it worked. So Alan would come in and he would say one of the words we wanted him to recognize. Say, 1. The loneliest number. We'd take a recording of that, and from that recording, we would calculate what's called the formant frequency. The formant frequency is basically just maths for look at all the frequencies that were produced and pick the loudest one. And we can represent that with the color orange. Then we go and do the number 2, and we get blue. Do the number 3, and get pink, and so on and so forth for the rest of the numbers up to 0, which we're not going to do because that would be boring. Once we've got those numbers, we can then repeat the whole process like 20 times. And each time that Alan says those words, he's going to pronounce them slightly differently because that's how human beings work. So we're going to end up with a range of frequencies that represent each number. And that's it, we're ready to go now. So Alan comes in, and he says the word 2. And it comes out as this light blue frequency that shows up really well on this screen. And Audrey recognizes it as the number 2. And that's it. It's really simple. It's just really basic pattern matching. It really did get 97 to 99% accuracy, but there were some limitations on the system, right? So if we were to grab another computer scientist at random, say Grace Hopper, Grace's voice is pitched differently to Alan's. So when she says the number 2, it comes out as pink. And Audrey incorrectly recognizes that as the number 3. So we could go back and retune the system so that it worked for Grace, but then it wouldn't work for Ellen anymore. It was pretty much a one-user system, which is, inconvenient, but there were also some more fundamental problems with this approach. So if you use a single frequency to represent each of the words in your vocabulary, you are going to run out of frequencies pretty quickly. And because formant frequency is really only distinguished between the vowels in a word, you're going to get a bit of overlap there. In Audrey's case, this wasn't such a big deal because the system really did only need to recognize 10 words. But it also failed to deal with something that's sort of a more fundamental problem in speech recognition, even for systems today. And that's working out where the words start and end. So when you've got written words, this is really easy, right? You start at the beginning, and that's the start of the first word. And you keep going through all the letters until you get to a space. And then that's the end of the first word. And then when you get to the end of the space, that's the start of the second word. And you keep going to the next space. Super simple. With spoken words, though, there's no spaces. In fact, this is a recording of someone saying, "Where are the silences?" And if you look there, there are silences. Sure, and it's not lined up properly. I blame Rick. But the only place there where a break between the words actually lines up with the silence in the recording is at the start of the word silences. And to be honest, the only reason that really happens is because s is a really quiet sound. So you can imagine for a computer system, it's really hard to tell if you've got a string like this, whether it's supposed to be 2 words or 3. So Audrey dealt with this problem basically by cheating. When you spoke to it, you had to pause between each word. Which, again, is probably fine when all you're doing is reading out a phone number, but it's not really a scalable solution. The good news is, modern systems have actually solved all of these problems. It might not seem like it when Siri does something dumb like this, but in reality, she's understood all the words that you've said. She's just got a little bit confused about what you meant. So really, the only reason that Audrey scores higher in accuracy ratings than the modern systems is that the modern systems are really solving much harder problems. Not only can they deal with multiple users, often at the same time, with no training, they have huge vocabularies, probably bigger than some people you know. And not only do they know where the words start and end, they can even work out the context of what you mean. So, how did we get from this system? How did we get from this system that could, really accurately recognize a total of 10 words spoken by a single user if they pause between each word, to something that, could potentially save your life? Well, if you really want to know, you're going to have to come to BuzzConf and watch my talk.